And so we have in the first session 2 speakers. The first one will be Michal Feldman from Tel-Aviv University, who will speak about auction design under interdependent values. So Michal, the stage is yours.
Thank you all for coming. So today I'll talk about auctions with interdependent values. I'll explain what I mean by this. And this is based on joint work with Alon Eden, Amos Fiat, who is here, Kira Goldner, and Anna Karlin. Okay, so I need both hands. Okay, so let's start with a question. How much would you be willing to pay for this piece of art? Any higher? 100 shekels. Okay, pretty good. 200. Okay, so about 200 shekels. Nice. How about this piece? More or less, about the same. What? Can't afford it. Can't afford it. Okay. So you already have some private information, right? Okay, so, so higher, I guess. Okay. Now suppose I tell you, and this is true, that this piece sells for $86 in Overstock.com, and this piece by Polak, the famous artist, was bought by a guy named David Martinez for $140 million. Would it change how you feel about the two pieces? No, okay. So for some, yes, for some, no, which is good. And in fact, actually, experts know that this is not the right position of this piece. It should be positioned vertically. And so how about now? And in fact, real experts know that this is not the right position either, but this is the right position. So it's very important. You know, for 140 million shekels, you want to position it right. Anyway, so I think it would be true to say that the most fundamental problem in the theory of auctions is how to sell a piece efficiently, meaning to give it, so, you know, I want to sell a piece and we have all this audience and they want to give it to the person who values it the most, where values are private. I don't know people's values. And arguably, we already have a solution. We can just run second price auction. Those of you who don't know, it's a very cute type of auction where the highest bid gets the piece and he sells the second highest bid. And this gives the right incentives for people to truthfully reveal their information. The problem is that this trick works only under the assumption that values are independent and private. There is no correlation between people's values, and I want to argue that this is usually not the case. Usually, you know, just like in the example that we showed before, that we saw before, usually, you know, if you have some private some information from others, it helps you form your own opinion and your own value, so people's valuations are highly correlated. And in order to study this setting, we adapt the interdependent value model of Milgrom and Weber from '82. Let me show you the model. It's a very simple model and very nice, which captures very general settings. So in this setting, every bidder has some private signal SI. This private signal captures some private information that agent I holds. And then every bidder also has some public valuation function, VI, which is a function not only of his own signal, but VI is a function of the signals of all agents. So again, signals, every agent holds a signal which is private, and then also some public valuation function, which is a function of all the signals of people. And valuations are monotone in all signals. And by the way, signals are drawn from some joint probability distribution which may be correlated. So we make no assumptions on this probability distribution from which those signals are drawn. So the first example is related to the example I showed you before, which is a value that is kind of resale value, where the value of agent I, given the signals of everybody, is some convex combination of the signals of people, and we have this beta ij, which is, how much agent I is affected by the opinion or by the private information of agent J for this piece. The second very common example is that of oil drilling, where different firms compete for the right to drill oil in some tract of land. And usually the value is common to all bidders, but it is unknown. And different firms run some tests, like geological tests, and they come with, those big cars, and they drill, and they gain some information about this unknown information, whether there is oil in the land, and if so, how much. And in this common value example, the effective value for all firms is the same, and it's the expected value given the signals that the different agents collected. So what's a mechanism in this world? So let's recall that signals are private, but valuations are public. And in this mechanism, unlike the mechanism for, so very similar to a mechanism for independent private values, people just submit their types. Here, their types is not their valuation, but their signal. The private piece is their signal. So the agents submit their private signals to the mechanism, S1 to Sn. And the mechanism returns two things, as always, allocation and payments. And these allocation function xi, how much agent I gets. If it's deterministic, then it's either 1 or 0. 1 means that the agent gets the piece, the item, and 0 it doesn't. And this is a function of all the signals collected from the agents. And the payments is just how much agent I pays. So for example, here is the mechanism. Here I show you just the allocation. So this matrix represents an allocation function. So you see on the x-axis the signal of agent 1. So agent Y1 has 4 different signals, and he reports one of them. And agent 2 has 3 different signals. And this matrix says, if, for example, agent 1 said my signal is 1, and agent 2 said my signal is 1, then this mechanism says agent 1 is the winner. Okay? And from this point on, throughout the talk, I'll use the color of red to represent agent 1, and the color of blue to represent agent 2. Okay? So red means that 1 wins. Blue means that 2 wins. So this is some allocation function. And now we want to discuss truthful mechanisms. Now the question of what's the right notion of truthful mechanisms for interdependent values is not very clear. And there are at least 3 relevant notions, going from a very robust one of dominant strategy incentive compatibility, IC stands for incentive compatibility, to less robust notion like Bayesian ICIR, and there is one in the middle. Now, in order to determine what's the right notion of truthfulness, we are going to use some guiding principles from mainly Wilson and other like Bergman and Morris. So Wilson writes that only by repeated weakening of common knowledge assumptions will the theory approximate reality. He says we can't really take too seriously the assumption of common knowledge. Everybody knows exactly the probability distributions of others and respond in a perfect way to this knowledge, full knowledge of people's distribution. And similarly, Bergman and Morris say that the mechanism design literature assumes too much common knowledge of the environment. And they actually give us a nice recipe of how to deal with it. They say the modeling strategy must be to first make explicit the implicit common knowledge assumptions and then weaken them. We can't really rely on everybody knowing everything, because this is too strong of an assumption. And this approach has been come to be known as Wilson's doctrine. It's a very well-known doctrine. And from now on, whenever I'll use these whenever I'll make modeling decisions that are inspired by these guiding principles, I'll use this approved stamp. Okay, so I'll try to weaken this common knowledge assumption and try to really come up with notions that do not assume too much common knowledge. Okay, good. So now we have a very, very nice and helpful characterization of, oh, wait, I skipped one. Okay, so arguably, given Wilson's doctrine, the right notion of truthfulness would be that of ex post. So IC stands for incentive compatible. This is really truthful, and IR is individually rational. It means that people also want to participate in my auction. So what's ex post IR, ex post IC? It means that truth-telling is an ex post equilibrium in my market. What does it mean, ex post equilibrium? It means that for every signal realization, truth-telling is the best response to truth-telling by others, okay? And this holds for every signal realization. So in particular, it means that agents do not need to have any knowledge whatsoever of the distribution from which signals are drawn, because it's irrelevant, it's for every signal. And also it has this very nice no-regret property, meaning that also after all the signals are revealed, people do not regret that they revealed their signal truthfully. So this is a nice notion. If we want to go this is weaker than dominant strategy, but dominant strategy is irrelevant in interdependent valuations. It's too strong. People don't even know their value because their value depends on other signals, so we can't expect them to just reveal their values truthfully in a dominant strategy, okay? So, okay, and if you want the formal definition, so this is ex post IC. It means that for every signal profile and for every SI, which is the real signal of the agent, and SI prime, which is some signal of the agent, the utility of agent I, which is quasi-linear, it's the difference between its value and the payment, is better if it tells the truth, and also that it's greater or equal than 0, so he wants to participate in my auction. Okay, so from now on, when I say truthful mechanism, I mean ex post IC and ex post IR. For every signal profile, truth-telling is an equilibrium. Good. Now I want to design truthful mechanisms. So I have a very helpful characterization. And this is, those of you who know Meyerson, it's really the analog of Meyerson for interdependent values, and it also uses a very, very similar proof. And this characterization says that we have a truthful allocation. And when I say truthful allocation, I mean an allocation for which I can merge it with some payments to make a truthful mechanism. Not every allocation can be made truthfully. And this characterization says that an allocation is truthful if and only if it's monotone. Okay, and if it's monotone, then payments are also uniquely defined or roughly uniquely defined, but let's put it aside. So essentially what this characterization does, it lets me reduce the task of designing a truthful mechanism, which is saying what's the allocation and what's the payment, to just design a monotone allocation. So I don't need to worry anymore about building a mechanism, thinking about payments. It just, now I have to think about the algorithmic problem of designing a monotone allocation. And that's it, and I'm done. I know how to set payments so that my mechanism would be truthful. And as I said before, it's very similar to what Meyerson did for independent private values. Okay, so just to make sure we are all on the same page, let me just make sure we all understand what's a monotone allocation. So an allocation is monotone if fixing the signals of all other bidders. As I increase the signal of agent I, his allocation can only increase. Okay, for example, let's look at this allocation function. We see that at this point 1 is the winner. So it's monotone because from the point 1 is the winner, it wins all the way when his signal increases. The same here. And the same thing for agent 2. Here is the winner, so he wins above. This allocation, for example, is not monotone because if, for example, we look at this row, then 1 is a winner here, but as he increases his signal, then suddenly he is a loser and 2 wins. Okay, and similarly for agent 2. So this is what I mean by a monotone allocation. So from this point on, my problem as a designer is just to design a monotone allocation. Okay, good. So now another property. As it turns out, single crossing is a crucial property that enables very nice results in the realm of interdependent values. And what is single crossing? So let me just say there are different versions, different notions of single crossing. The one that I'm going to use in this talk is the one that takes derivative terms. And what it says is that if I look at the derivative of vi as a function of si, it's greater than the derivative of any other agent's value vj as a function of si. In other words, bidder i's signal si, a change in bidder i's signal, affects bidder i's value more than it affects other people's values.
Question.
Yeah.
Didn't you insist that the signals are discrete? So what is exactly the meaning of the derivative?
Okay, so very good question. So in the first part of my talk, insist my signals will be discrete, and in this sense, I just take the difference. So the difference in value. So because they are discrete, let's just assume without loss of generality that these are just integers. So I look at the difference between vi, where si and si plus 1. Good question, thank you. Any other question about the model? Yeah.
You're assuming the signals are ordered or something. You didn't assume that in the beginning, right?
That?
The signals are somehow linearly ordered.
This was important even for monotonicity.
Yeah. They are right. Okay, and essentially all the work, there is a lot of work on interdependent values, mainly in economics. And essentially, every single piece that we found uses these single crossing assumptions. It's very, very common. Pictorially, the way to look, and again, this is indeed discrete, so we can't draw, but just let's imagine it's continuous. And what it means pictorially is that if we draw the curves of agent i's value, which is the red curve, and agent 2's value, which is the blue curve, then the slope as a function of S1 of the blue guy, then the slope will always be greater for the red curve than for the blue curve. Now, what's good about single crossing? So single crossing, in fact, enables full efficiency. So VCG is the general mechanism that we have for independent private value, and we have an analog if we have single crossing, and again, we are talking now only about selling a single item. If we have single crossing, then we have a mechanism called generalized VCG. I'm not going to tell you the details, but it's very simple and very, very similar to VCG, and I can just implement full efficiency, meaning I can give the piece, the item, to the agent who values it most, which is very nice. And by the way, GVCG, remember this stamp, GVCG is prior free, which means that the mechanism rules do not use at all the probability distributions. The mechanism designer doesn't need to know anything about the probability distributions, and the rules of the mechanism do not depend on the probability distributions. So we call it prior free mechanism. Yes?
The derivative condition ensures single crossing, but you could have the single crossing without the derivative condition.
Yeah, very true. So as I said before, there are different notions of single crossing. The one that I'm using here is pretty strong. And you are right that in terms of characterization, it's the single crossing thing or a variant of it that characterizes when full efficiency can be implemented. But I'm going to use this definition, which is indeed stronger than the single crossing property pictorially. Thanks. Okay, so we really like this prior free thing because of Wilson's doctrine. And what we want to do is imitate this prior free design, and we'll see how we do it. Okay, without single crossing, unfortunately, the highest valued agent is not implementable in general, and the problem is that many natural examples are not single crossing. So single crossing is nice because it enables full efficiency, but many examples are not single crossing. For example, here is an example from a very well-known paper by Dasgupta and Maskin from 2000, In this case, again, we have an oil drilling example where two firms are competing for the right to drill oil in some land. Unlike before, their values are, so again, their values depend on the signals of the different agents, but not in an identical way. So let's suppose in this, and this is the example that Dasgupta and Muskin give, that firm 1 performs a private test, and only firm 1 performs a test, and it discovers that the expected size of the oil reserves is S1 unit. And let's also suppose that oil can be sold in the market for a price of 4. So what would be the values of the different firms? Let's also assume that each of the firm has some fixed cost for drilling and marginal cost for drilling. And firm 1 has fixed cost of 1 and marginal cost of 2. So its value is 4 minus 2. This is what it gets for every unit of oil, and 2 is the marginal cost times S1, the units of oil, minus 1. This is the fixed cost, which is 2S1 minus 1. And similarly, the value of firm 2 for the oil is 3S1 minus 2. So this is not single crossing. We see that the effect of S1 is greater for firm 2 than for firm 1, and there are many examples where single crossing simply does not hold, and the literature just doesn't let us know what to do with such examples. So this is where we start, and our goal is to design good prior free mechanisms for settings without single crossing, and the approach, of course, that we are going to take is approximate efficiency, because we cannot do full efficiency, and this is approximation is the trick that computer scientists have in comparison to economists. So economists usually say it's implementable or it's not implementable. We have the power of approximation that lets us do many interesting things that didn't exist before. Okay, and again, also our approximation notion will again be prior free approximation, and meaning that we require the approximation to hold for every signal profile, not in expectation over signals knowing the probability distribution, but for every signal profile S, we want the expected welfare of our mechanism to be at least 1 over alpha of the maximum welfare. And this, if it holds, we say that the mechanism is prior free alpha approximation, or just alpha approximation. Okay, so we have this notion of approximation, and now the question, what can we do with it? We have a few discouraging observations. First of all, we realize that every deterministic prior free mechanism can be arbitrarily bad. So it's nice that we have this, approximation tool, but we cannot do anything with it. Every single mechanism may be arbitrarily bad. And just to give you the intuition for how to think about these settings, let's prove it. So suppose we have some R such that better than R approximation is possible. And let's look at this example, at this setting where we have two agents, 1 and 2. Agent 1 has 2 possible signals. S1 is either 0 or 1, and S2 is always 0. So only S1 matters here. And the values in the different profiles, so remember, values are function of signals. So if, in this case, where S1 is 0 and S2 is 0, the values are R and 1. And in this cell, it's R and R squared. OK, so if we want to give better than R approximation, we better allocate the item to the red guy, to agent I here, because he is factor R better. His value is factor R higher. And now, the crucial thing, remember, in order to design a truthful mechanism, the only thing that we need to care about is that the allocation is monotone. What does it mean here that the allocation is monotone? If we allocate to the red guy here, we must allocate also to the red guy here, because it's this guy's signal that increased. And here we lose the factor R. Okay, so we cannot do better than our approximation, so we can't do anything deterministically. So now we say, okay, what about a random mechanism? The other discouraging fact is that even a random, we can't really design any smart random mechanism. So of course, with a random mechanism, we can just allocate the item to a random guy, and this will give us n approximation, and essentially we cannot do anything better than that. Okay? Now, I don't want to go through the example that shows that we cannot do better than n approximation, but the only thing I want to tell you is that in this example, there are two things going on. So let me just tell you just a hint about the example. In this example, agent 1 value is 0 until the point, so all signals are binary here, and agent i's value is 0 until the point that all other agents have signal 1, in which case he is happy. He has value 1. So what's going on in this example, in this bad example? Two things. First of all, first of all, it's not only that the valuations are not single crossing, they are highly non-single crossing. Agent i's value, not only that his signal does not affect him more, he doesn't care at all about his signal. He only cares about other people's signals, so it's not single crossing at all. The other thing is that signals are highly complementary. As long as not all the signals of other agents are 1, the value of agent I does not change, and at the point where all of them become 1, then suddenly agent i's value jumps to 1. So two things, they are highly non-single crossing and highly complementary. So what we are going to do is consider valuations that are not too far from single crossing or not too complementary. And this is exactly the approach that we are going to take. So our goal is to map this interdependent universe. We already have 2 points. We know that in general, we have some instance where we cannot do any finite approximation with a deterministic mechanism, and we know that we cannot do better approximation than n in any random mechanism. We also have this class of single crossing valuations for which we can do full efficiency. And okay, so now where are we, what are we doing? So first of all, we introduce this parameterized version of single crossing. It's a relaxed version of single crossing where C is the parameter that quantifies how far we are from single crossing, and in a minute I'll show you formally what I mean by this. And what we try, do you see this circle of this single crossing? It's pretty light, but I hope you can see it. And what we want to check is whether the nice properties of this class single crossing degrade gracefully as we move away from this class. Okay. The other class that we study is what we call submodular over signals. Valuations are submodular over signals. And again, I'll show you the definition later, but what it means is that the signals are not too complementary. And again, we also study this parameterized version of submodular over signals. Okay, so this C single crossing thing appeared in a paper in EC 18. And this work on submodular over signals is part of some work in progress. Okay, so first of all, what's relaxed single crossing, C single crossing? So if you remember, this is without the C. It's exactly the definition of single crossing that we had before. And now we just say, okay, maybe VI is not affected, does not have the highest effect when SI changes, but factor C. Okay, so this is what we mean by C single crossing. So it means that one sensitivity to his signal is significant. Maybe it's not highest, but it's significant compared to others. So let's see an example that is not C single crossing. So let's look here. So here S1 signal increased, V1 increased by 1, and V2 increased by 2C. So it's more than C times more than the change in V1, so this is not C single crossing. And let's go back to this example. So before, all we could say about this example is that it's not single crossing. Now we have a way to measure how much single crossing it is, and it is 1.5 single crossing. Okay, so we have a parameter that measures, that quantifies how far we are from single crossing. And what we want to do is provide approximation results for valuations that are C single crossing. So what are our results? So for settings with 2 bidders and any number of signals, of discrete signals, and for settings with 2 signals and any number of bidders, we have C approximation mechanisms. And this is tight. C approximation is tight. Even for settings with 2 bidders and 2 signals each, you cannot do better than C approximation, and we give C approximation. So here we are tight. Here we have some results, but it's quite embarrassing, because what we can show, we have a deterministic mechanism that give us order NC approximation, or randomly we can get it down to root n times c to the 3/2. But really, we don't know at all. We don't know even if the approximation ratio needs to depend on n. Maybe it's just order c, and this is the big open problem that still remains from this work. Okay, so what I'm going, from all these results, I'm going to show you one result with proof, okay? So what I'm going to show you is that if we have any number of agents, and every agent has a binary signal, either 0 or 1, and valuations are C single crossing, then we can get C approximation mechanism. Okay, so a key lemma, which is a direct implication of C single crossing, is the following. We call it approximation preservation lemma, and it's a very simple lemma. What it says is that if V1 C approximates V2 in this cell, then because of C single crossing, it keeps C approximating V2 as S1 increases, keeping all other signals the same. Okay, very simple. The proof is very simple, just 2 lines of algebra. Okay, so let's remember this. And the contrapositive of this lemma is that if V1 does not C approximate V2 here, it does not C approximate V2 for lower signals. And we are going to use both ways. Okay, so now I'm going to show you the mechanism. So now I'm going to use a slightly different representation of, because I have more than 2 agents. So this is the hypercube of signals. And what we see here, every node in this hypercube is just a signal profile. And we have 4 agents, red, blue, green, and orange, S1, S2, S3, S4. And we don't see the values here, we just see the signals here. And we have an arrow from one node to another node if their Hamming distance is 1. So some agents changed from signal 0 to signal 1. So again, we have n agents, and every agent has a binary signal, 0 or 1, and every arrow here belongs to some agent. The dimension is of some agent. Okay, so before presenting you the mechanism, let me give you the intuition for it. So remember, here is the mechanism. Just for every signal profile, let's allocate the item to the guy with the highest value. That would be full efficiency. Why can't I do it? Because my allocation must be monotone. So what's the restriction that I have? If I allocate the item to a guy when he has a low signal, I must allocate the item to this guy when his signal increases. So this is the monotonicity condition that limits me. So what do I want to do? I want to try as much as possible to allocate the item to agents with high signals. Because when I allocate an item to an agent with a high signal, it doesn't limit me at all. It's only when I allocate the item to an agent with a low signal, it limits me by the monotonicity condition that I must keep allocating to this agent when his signal increases. Okay, so this is the guiding idea. And here is the mechanism, very simple. Maybe the first thing you would think about, it's a deterministic and simple mechanism. We go over the profile in increasing Hamming weight. And what we do is the following. We want to allocate the item to a high signaled agent. So we check. If the highest valued high signaled agent C approximates the agent with the maximum value, we allocate to this guy. Otherwise, we allocate to the maximum agent who has low Otherwise, we allocate to the maximum agent who has low signal, but then we must propagate the allocation, right? Because we must satisfy monotonicity. This is the only condition that matters. Okay, let's see an example. So we look at this profile here, everybody is low. Let's say agent 1, the red guy, has the highest value. We allocate to the red guy and propagate. We must propagate. Okay. Then we keep going to the next one. Here, blue is the high signal. And let's say that it is the approximation to the maximum value. So we allocate to the blue guy, and that's it. We don't need to propagate because he has high signal. We keep going, and here green is the highest signal, but let's say he doesn't see approximate the highest value. So we allocate to the blue guy, who is the highest value, and then we have to propagate, and so on and so forth. And this way we just color the whole hypercube. One small remark, coloring the whole hypercube is, of course, an exponential operation, but really we have a mechanism. This exact mechanism can be implemented in polynomial time. Yeah?
Since you keep going back and forth between continuous and discrete, what will you do in the continuous case? Because the propagation is not clear.
You are right. So in this case, I only consider discrete signals. So in this, we might have an extension, but not yet. Okay, it's not clear if we can extend it. Okay, but indeed this is discrete. Okay, so now I want to convince you of two things. First of all, that it indeed gives me C approximation, and second, that it's monotone. So why does it give me C approximation? There are three cases. Either I allocate to a high signal who C approximates the max value, so of course it's C approximation. Or I allocate to a guy with a low signal who has the maximum value, of course it's C approximation. Or I allocated, my allocation resulted from a propagation from the maximum valued agent, in which case I use the approximation preservation lemma to tell me that also after the propagation, I have C approximation, so the C approximation is good. Okay, what about monotonicity? Well, monotonicity holds by design, because whenever I allocate to a guy with low signal, I propagate it. So I satisfy monotonicity by design. So am I done? Do you see any problem? Exactly. I might have a propagation conflict. Maybe I propagated red from one side and blue from another side, and now what do I do? So I need to also to show you that in my mechanism there are no propagation conflicts. Okay? So this thing is, zooming in from this whole hypercube, and let's assume that we have a problem of propagation conflict. What does it mean? It means that here the red guy is the low signal, and I colored it red, so it propagated. And in the other one, blue is the low signal, and I colored it blue, and it propagated. And then I have a conflict up there. So I want to show you that this cannot happen. Why it cannot happen? Why did I color it red? Using my mechanism, the only reason to color it red is if 2, who is the high signaled agent, does not see approximate V1. But then, by the contrapositive of the approximation preservation lemma, V2 does not see approximate V1 down here either. Similarly, why did I color this blue? Because V1 did not see approximate V2 there, and again, by the same lemma, it doesn't see approximate V2 here, and then we have a contradiction because one of them is higher. Okay, so this means that indeed I don't have propagation conflicts, and this mechanism gives the approximation. Okay, so in particular, if we go back to this example, before our work, we couldn't say anything except we cannot implement full efficiency because it's not single crossing. Now we have a way to argue about how much single crossing it is. It is 1.5 single crossing, so we can get 2/3 of opt by a truthful mechanism. Okay, now in the 10 minutes remaining, let me talk with you a little bit about this other notion of submodularity over signals. So we consider this property, which I'll define you shortly, and what we show is that if our valuations are submodular over signals, we can always get 4 approximation. And if we have d submodular over signals, then it extends to 2 times d plus 1 approximation. Now, the one thing that I want to emphasize here is that when we go to, so with this C single crossing thing, the whole thing was about a single item scenario. When we move to this submodularity notion, the results extend way beyond single item settings, and in fact, we have very general results. The same 4 approximation results extends all the way to very general combinatorial auction setting. In fact, general combinatorial auction setting with general valuations, where agents just have different valuation for every bundle of items under some mild assumptions, which I'll show you. Okay, so what does it mean to have valuations that are submodular over signals? What it means is that when the signals S minus J, the signals of all other agents except for one agent J, are lower, the sensitivity of some agent's value to the signal of agent J is higher. Okay, so think about it again. When all signals are lower, the effect of some signals on me is very high. Whereas where all signals are higher, the effect is lower. This is what we call submodularity over signals, and this happens a lot. Like many examples that we think about, including the common value, resale, oil drilling, wallet game, many examples satisfy this submodularity over signals condition. And again, if we want to do D submodular, we just have this factor D, just like we had for C. Okay, good. Okay, what's the key lemma for submodular valuations? Keep changing hands. Okay, so here is the key lemma. Let VI be a submodular over signals valuations. Now let's split all the agents other than some agent I into 2 random sets. So uniformly at random, every agent is either in set A or in set B. And now consider the following signal profile. Let's just look at the signal profile, but zeroing out all the signals of agents in B. Okay, so we take the signals of agents in A, we call it SA, but we zero out the signals of agent in B. Now, what the lemma tells me is that in expectation over the choice of the set A, the value of agent A under this signal ignoring B, when I zero out all the signals in B, is at least half of his real value, under the real signal profile where everybody has their signals. Okay? I'm not going to show you the proof, but the proof uses very strongly exactly this submodularity notion, plus some coupling arguments, and so we have it. Okay, good. And then for D submodular, it extends, instead of the 1/2, we end 1 over D plus 1. So now, for a single agent, the mechanism is as follows. We partition the agents into 2 sets, A and B uniformly at random. And what we do is we allocate the item to the bidder I in B. We never allocate to agents in A. We look at the agents I in B, and we allocate to the bidder I in B whose value under these values ignoring B's signal is highest. Okay? This is the mechanism, and what we claim is that this mechanism is monotone. It's easy to see, and also that it gives 4 approximation for submodular valuations, and this is almost immediate from the key lemma. Okay, so for a single item auction, we know how to give 4 approximation if we have submodular valuations. Okay, good. Now, as I said before, the nice thing about submodularity is that it extends way beyond single item auctions. And in fact, we have positive results for different scenarios. So maybe I'll just give you really a taste of unit demand valuations, and then I'll say a few words about general combinatorial auctions, and then I'll end. Any questions? Yeah.
Small question about your definition of monotonicity in the previous slide. Since the allocation...
Of monotonicity or submodularity?
Go back to the previous one, the monotonicity. So you divide it into 2 sets randomly.
Yeah.
And this is with high probability, it's monotonic, it's...
No, it's not with high probability, it's just monotone, because agents in A never get the items.
But the partition could be extremely lopsided, that A is empty and B is everything.
That's fine. That's fine. What I need to show is that it's monotone for both for every agent in A, and it's monotone for every agent.
Monotonicity when you are doing some randomization, and then you are talking about monotonicity of the result. Is it?
So for every realization of this, for this partition, it's monotone. Okay, thank you. Okay. So what's unit demand valuations? So here we assume that every agent has a signal, Si, which is a real value. And every agent also has some value for every item. So we have these Vij valuations, the value of agent I for item J. And the first observation that we make, remember this single crossing property that was really the golden condition in essentially all the works of interdependent values. It totally breaks when we go beyond single item. So even in this very, very simple case of unit demand value, so by the way, unit demand valuations, what it means is that I have a value, I'm agent I have value for every item, and then if you give me a set of items, my value is just my highest value for any item in the set. It means that I go home with a single item. So if you give me more, I just take my highest value. Okay, so this is a very, very simple setting. I have only 2 items and 2 agents. And only one agent has 2 possible signals. And I'm not going to go over this example, but believe me that this example is single crossing. And in this example, already I cannot implement opt. So this is opt here, and this is opt here. X is large. I cannot implement opt. This is not truthful, and therefore, I must, either in this one or in this one, I'll lose half the welfare. So I can do at most half of opt, even in this very simple case. So single crossing is not really the right notion when we go beyond single item. Okay, this is the main message of this slide. Okay, so what can we do? We show that if valuations are submodular over signals and we have unit demand valuations, then if the signals are binary, we can still do for approximation. And if we have at most k signals, here again the signals are discrete, then we can do order k or k plus 3 approximation. I'll just say a few words about it. As opposed to the single item case where we had a very clean characterization of truthful if and only if monotone, here we don't have a simple characterization, so we really go to basic elements in order to design truthful mechanisms. So we design the mechanisms like we design the allocation and payments and show that they are truthful. And the mechanism are some variants of the random sampling Vickrey auction that I showed you before. So really it all goes back to this key lemma of submodularity, that the expected value of an agent ignoring agents in B is at least a half of his real value. Okay, so these are all variants of it, and we can do some nice approximation. Now for general combinatorial auctions, so let me first tell you what I mean by general combinatorial auctions. So we have n agents and m items. Every agent has a signal for every bundle. So Si is now not a real number, but a vector of SIT for every subset T of M, the set of items. And the value of agent I for bundle T is some function of all the signals of all the agents for this bundle T. Okay? And okay, so now what is the assumption under which our mechanism works? We assume that valuations are separable, meaning that VIT of signals S can be separated into some function GIT that depends only on signals of others, plus some function FIT, which is a function only of my signal. Okay, and again, many natural valuations are separable, and our canonical example is the resale example, which is completely separable. And what we show is that this random sampling VCG, so it's very similar to the previous mechanism that we had for a single item, What it does is partitions the agents into two sets A, B uniformly at random. And then, again, it looks only on agents I in B. It ignores agents in A. And for every I in B, it looks at the values, again, ignoring the signals of agents in B. It only looks at the signals of A and I. And then it finds the maximum welfare allocation for these fake values, okay, for these values ignoring B. And then, just like I said before, we don't have a characterization, so we also have to specify the payments, and the payments are VCG-like, for those of you who know what I mean by VCG. Okay, so some critical values that make the whole mechanism truthful. And what we show is that this random sampling VCG is a truthful mechanism that gives 4 approximation for any combinatorial auction setting with separable valuations. Okay, so now let me summarize. So first of all, I believe that this is the real world that we should study. Valuations in the real world are correlated, and interdependent values is probably a good model to start with. So we want to study combinatorial auctions with interdependent values. What have we done so far in our community? So one thing we have studied is this really, really tiny, I mean, here I just wanted it to show, but it's really, really tiny region within this whole region, which is independent private values. So essentially, 99% of the work in AGT, in CS, is about independent private values. This is really tiny. The other region that we looked at is single item, which is really very, very tiny again, and within it, it's single crossing, and we know what to do, and we are left with all this region to study. So our goal is to do some work for these unexplored regions within this huge world. And what we did in these 2 works is provide approximation guarantees, first of all, for combinatorial auctions with submodular over signals. So part of the contribution is in introducing this property, which we believe is crucial and very helpful for interdependent values. And then for single item auctions, we extended some work from single crossing to this parameterized version of single crossing, which we called C single crossing, and gave some approximation results. Thank you.
The notion that the whole value function, my value, which depends on other people, that's public, seems pretty strong, isn't it?
I agree. Yeah, I don't have anything to add. You are right. So, okay, so Chandra's point is that, I talked about Wilson's doctrine and how important it is not to make too strong assumptions about common knowledge, and yet I assume that valuations are public given signals. It's true, it would be very nice to get rid of this strong assumption. This is a first step, but I agree.
So one quick clarification for me, perhaps I missed something. At first you said that every bidder has a signal, but then you separated the 2 parameters. You said N bidders and K signals. So is it possible that some bidders will not produce signals?
Sorry, so I didn't mean K signals. What I meant is that the signal of every agent is one of K possible values.